all this talk about identities. And the question is, which ones do we really need? Do I have to memorize all of them? You know, you should always never assume, right, when you're in an exam kind of situation that you won't have a formula sheet. And of course, in exam conditions, right, the question should be doable for you in that moment, right? No professor would give an exam that is overly difficult for the time period. So we're going to go through some of the basic identities that you'll need to know, ones that you should have in your back pocket at all times, and then how you can probably reconstruct some of them. Okay, this is going to be a very fast one. And the fun thing is, you can, if you ever need a reference when you study, well, you can always do a Google search like trigonometric identities, cheat sheet, or something, and you might get something that looks like this. This is actually the exact same one that I gave to my 11th graders when I taught pre-calculus. And when I started this unit, I printed up this in a giant poster, put it in the back of the room. Everybody had one of these, and we always had some variant of this in a shortened form on our exam papers. Okay, but for calculus, of course, it is assumed that you know most of these or all of these and how to get there, but you won't always need all of them. And especially when you talk about integration, you don't need every single one of these identities. But the question is, which ones should you know? So this is just the top half of this. And if we scroll through, well, we see that there's a lot here, right? We got difference of angles, double angle, even odd, cofunction, power reduction, product of sum, but we don't need all of them. That's the thing. We don't really need them all. But which ones do we do? So first off, everything up here, the reciprocal identities, the quotient identities, and the Pythagorean identities, all of those you must know like the back of your hand. Okay, the reciprocal identities actually follow, okay, from thinking about this in the classical sense where you think about a right triangle, right? Sine and cosecant are reciprocals, right? Sine is opposite over hypotenuse, so that makes cosecant the reciprocal, hypotenuse over opposite. Once you have the sine, you got the cosecant for free, and conversely. Okay, tangent and cotangent in a similar way. They are reciprocals. You can always get one from the other. Now, the quotient identities, tangent is sine over cosine. Well, you can kind of verify this for yourself. Just do some of the fraction work and you'll see it. This is actually useful when you do things with vectors and polar coordinates, but you can always reconstruct this. In fact, sine or cosine are like the basic functions. They're the most basic ones. And you can always write everything in terms of sines and cosines whenever you solve a problem. That's the general strategy that I give to folks when they're starting out with those. I call them trig identity puzzles. Anytime you're trying to see if an identity holds, just try to write it out in terms of sines and cosines. See if stuff cancels. Okay, cotangent is a similar way. It's cosine over sine, and that makes sense because, cotangent is a reciprocal of tangent, so we use those right away. Now, the granddaddy identity here, the one that everyone should know, everybody should know this one. Sine squared plus cosine squared equals 1. It doesn't matter what the angle is in there so long as they are the same. You take the sine of an angle and square it, cosine of that angle and square it, add them together, you get 1. And that's the most basic identity everyone knows. In fact, it's so Pythagorean identity because this kind of looks like the Pythagorean theorem, just about. Now, everything else can be derived from this. Okay, if for example you subtract, let's see, if you subtract cosine squared from both sides, you get sine squared. Let's actually write that down. Okay, so we'll do a different color here. So if you subtract sine squared on both sides, you get that cosine square theta is equal to 1 minus sine square. And then if you divide both sides by, say, cosine squared, well, you arrive at the second one here. Tangent squared plus 1 equals secant squared. All right. Of course, you can rearrange this to say tangent squared is equal to secant squared minus 1. Okay, just because an identity is not in the form that you have it doesn't mean you can't rearrange it just by using basic algebra. Just remember, combine like terms, okay? And make sure you have your minus signs on track too. Now, if you do the similar thing here and instead divide by sine squared instead of cosine squared, well, then you get this one here. Cotangent squared plus 1 equals cosecant squared. They're cousins. Okay. So everything in this box you should have in your back pocket, especially sine squared plus cosine squared equals 1. That identity gets used so much. Now, The co-function identities, you don't really need to know those. Those just tell you how to relate with the co-functions, sine and cosine, cosine and sine, secant and cosecant, tangent and cotangent. But what does the co mean? Well, co means complement, okay? And if you remember from high school geometry, two complementary angles are those that add to 90 degrees. So this is what happens if you have like an angle and its complement. So theta, 90 minus theta. Or if you're talking in radians, s'il vous plaît, theta and pi over 2 minus theta. So this just tells you how to relate the co-functions together. You may not need these. The even odd identities are also ones that you may not need, but they just tell you how some of the functions behave, even in odd symmetries. And that is just based off the shape of the graphs. But we won't really use those as much. Now, the sum and difference formulas here, you also don't really need as much, okay? But they are still nice to know. Note that sine and cosine and tangent are not linear. You cannot distribute them. And that's saying that sine of A plus B is not the same as sine of A plus sine of B, okay? Sine is a function, not a scalar, so you can't distribute, okay? There are special rules that you have to follow here. Okay, there are ways to derive these using geometry, or if you're clever, complex numbers, which I do have a video on that, on how to derive that. But you don't really need those for a lot of integration that you'll do in calculus, although they're still nice to have just in case you need them. Now, the double angle identities, okay, this first one's very easy. Sine 2 theta is 2 sine theta cosine theta. I think that's a very easy one to remember. You've used this quite often, in my opinion. The cosine double angle formulas, notice that there's three because you can always rewrite sine and cosine square in terms of each other. It's just depending on which one seems convenient. In fact, you may not even need to use some of these, but you may need these two here, the 1 minus 2 sine squared form and the 2 cosine squared minus 1 form. Why? Because they show up here in the half angle identities here. Okay, we can kind of neglect the plus minus in front of the square root for the time being. That just depends on what value makes sense for your angle. Okay, but notice that you can always grab that just by solving for sine and cosine. Notice that you have a half angle, cosine of half the angle. You can express that in terms of cosine of the original angle. Same for the sine of half the angle. Okay, the formulas for the tangent half angle formulas, we may not need that. And also, we probably don't really need the tangent 2 theta formula there. Now, these power-reducing identities just come from rearranging the half-angle formulas, but we do need these. We do need the sine and cosine ones, okay? Notice that in the sine and cosine, okay, the sine SIGN in front of the cosine 2 theta term does matter, okay? When changing from sine square, okay, to power reduce, you'll have a minus. Cosine square, you'll have a plus, okay? Keep this handy. These product sum and sum to product identities don't get used a lot, I'll say, but if you are, say, in electrical or computing engineering and have to do anything with like signal processing, or you're studying like the Fourier transform, or just working with a lot of digital signals, these show up in a lot of integrals and a lot of formulas that you have. So unless you're doing that kind of application for a general purpose calculus course, you don't really need these formulas. But all these ones that I've highlighted here, and of course, those at the top, those are the most important ones to know. These should be in your back pocket. They're very easy to keep track of. Whereas the double and half angle formulas and the power reduction formulas, okay, those you may have to like have at your side whenever you're doing a problem. Okay, so think about this when you do integrals with powers of sine and cosine, and as a consequence, powers of secant and tangent and cosecant and cotangent. Okay, and especially when you have to use those sine and cosine square power reducing formulas. Okay, because those get used a lot and it's easy to get them mixed up. So do yourself a favor, have those handy. You'll be able to do it. You'll be able to find your way through.